In lesson 15.5, we're going to look at some slightly more complicated probability problems where we're going to use tree diagrams to help us organize the information in the problem and calculate some probabilities. And in the past, we've used two-way tables as a way to display the relationship between two categorical variables. However, sometimes we're given conditional probabilities, and in this case, it's more helpful to use a tree diagram. We're going to look at an example of tennis, where in tennis, players who are serving have two chances to serve to get to start the volley and to get the serve into play. And because a player has two chances, the player is often more aggressive on their first serve, because if they serve really aggressively, then the opposing player has less of a chance to return it. However, when they do serve more aggressively, sometimes the ball goes out of bounds, and then that's considered a fault. And then the player will get a second chance to serve where they are often less aggressive, and that means that the ball is more likely to be returned by their opponent. So anyway, in a recent season, Roger Federer made 63% of his first serves. And it says when the first serve was good, he won the point 78% of the time. When the first serve was not good and he had a second chance to serve, he only won the point 57% of the time. So notice the probabilities of him winning the point depend on whether he made the first serve or not. We're going to use a tree diagram to kind of map out all these different possible outcomes. So notice the first branch there, we have either the first serve is good or the first serve is a fault, meaning that it's not good. And they tell us in the problem that 63% of his first serves were good. Well, if there's a 63% chance that the first serve is good, that means that 1 minus that, or 0.37, is the probability that the first serve is a fault. And that number is not given in the problem, but we will need it, so I'm going to write it on that branch. Now, depending on what happens with the serve, he's either going to win the point or lose the point. And they tell us that when the first serve is good, the probability that he wins the point is 0.78. That means that the probability he loses the point would be 0.22. They also tell us in the problem that when the first serve is not good and he has a fault, he only wins the point 57% of the time. So 1 minus that gives us a probability of 0.43 that he loses the point. Now, in this case, we're going to apply what's called the general multiplication rule to find the probability of each of those outcomes. And what this rule says is that for all events A and B, the probability of A and B both occurring is the probability of event A times the probability of event B, given that event A already occurred. So now let's apply that to this chart. Over here to the side, I'm going to write down the outcome that that branch represents. Okay, that set of branches there where you take the top branch in each set, where the first serve is good and he wins the point, I'm going to write that as good and win. So over here, the first serve being good represents event A. Him winning the point, given that the first serve is good, represents the probability of B given A. And now to find the probability of both of those events occurring, which is the first serve is good and he wins the point, would be the product of those two probabilities. So 0.63 times 0.78, which gives us 0.4914. Now we can repeat that process for the other three branches in the chart. And for each one, I'm going to write down the outcome and then calculate its probability. So this branch would represent the first serve is good and he loses the point. This branch represents the first serve is a fault and he wins the point. And this one represents the first serve is a fault and he loses the point. So those are the four possible outcomes. And in each case, we're going to multiply the branches that we take to get there. So for good and lose the point, because we are going along this branch and then down to this branch over here, those would be the numbers that we would multiply together. So that product is 0.1386. Fault and win would be 0.37 times 0.57. Fault and lose would be 0.37 times 0.43. So we have four outcomes, four probabilities. And notice, by the way, if you go back and you add these four final probabilities together, you should get a grand total of 1 because that represents the entire sample space. If you get something other than 1, that means you either multiplied wrong or one of the numbers on your branches is wrong. All right, let's look at another example. Suppose that 5% of current NFL players are using steroids or other performance-enhancing drugs, which we abbreviate PEDs. Unfortunately, we know that tests to detect performance-enhancing drugs are not perfect. We think that 3% of players who are not using PEDs will test positive. So that would be a false result from the test or an incorrect result. While 1% of players who are using performing enhancing drugs will test negative and escape detection. So we know the probabilities that the test results come back wrong. And we're going to suppose that we're selecting one player randomly for drug testing. We're going to use a tree diagram to help us come up with all the possible outcomes and their probabilities. So in the first set of branches, we know that the player will either be using performance-enhancing drugs or they will not. Now, the second set of branches would represent our test results. So the player is either going to test positive or test negative. Now we can fill in the probabilities. We're going to start with the ones that they give us in the problem and then go back and fill in the rest. We know that 5% of players use performance-enhancing drugs. We are also told that 3% of the players who don't use them will test positive. And we know that 1% of players who don't use performance-enhancing drugs will test negative. So therefore, we can go back and find the other missing probabilities, knowing that in each case, each set of branches should total 100%. So if we have 5% that use performance-enhancing drugs, the percent that would go down here would be 1 minus that value. And if 1% here will test positive, that means 99% here, or I'm sorry, 1% test negative, that means 1 minus that, or 99% will test positive. So just by doing some quick math, we can fill in the rest of those branches. Now we're going to go ahead and list the 4 possible outcomes. So the 4 outcomes are: they use performance-enhancing drugs and test positive, they use and test negative, they don't use performance-enhancing drugs and test positive, or they don't use and test negative. And just like we did in example 1, we'll multiply along each of those branches to find the corresponding probabilities. And go ahead and pause the video if you need some time to write that down or finish those calculations. Now, based on this tree diagram, we're going to answer some questions. Question A says, find the probability that a player tests positive. Let's go back and look at our tree diagram again. We actually have 2 branches of the 4 where a player would test positive. Either they use performance-enhancing drugs and test positive, which is 0.0495, or they don't use and test positive, which means that probability of that is 0.0285. And because either one or the other could occur and lead to a positive test, we're going to add the probabilities on those 2 branches together. So 0.0495 plus 0.0285 gives us an overall probability of testing positive at 0.078. Player B is asking, or part B rather, is asking us to calculate a conditional probability. What's the probability a player uses performance-enhancing drugs given that they test positive? So in other words, if a player comes back with a positive test, what's the probability they actually use performance-enhancing drugs? The formula that we've had for conditional probabilities would look like this. We need the probability that they use performance-enhancing drugs and test positive, divided that by the total probability that they test positive. Well, use performance-enhancing drugs and test positive is one of the branches in our tree diagram that we calculated. That's the top branch of 0.0495. The denominator is what we calculated in part A. That's the 0.078. And so if we divide those, that will give us an overall probability of 0.6346. Example number 3. This would be a good one for you to kind of read and try and pause the video while you're doing that. And then when you replay the video, I'm going to go through it very quickly, and then you can stop and fill in any missing parts that you need. But here we're looking at a soccer goalie where during shootout situations, the goalies try to cheat to one side. So for example, before the ball is even kicked, the goalie kind of lunges in one direction or another, anticipating that the player who's kicking the ball is going to kick to the right or to the left. In a shootout, the coach tells the goalie that he should cheat to the right 60% of the time. Maybe just based on knowledge, the coach has observed that that's most of the time, that's the way that the ball is going to go. When the goalie cheats to the right, players make the shot about 50% of the time. But when the goalie cheats to the left, they make the shot 70% of the time. Here's what that tree diagram looks like. Here are the corresponding probabilities. Here are the outcomes with each of their final probabilities. And now we can answer the questions. The probability that a player makes the shot would be the sum of the two branches where the player makes the shot. The probability that the goalie cheats left, given that the player makes the shot. We need the probability that the goalie cheats left and player makes the shot divided by the total probability that the player makes the shot. We take that one branch, 0.28, and we divide it by the total probability that they make the shot, which we calculated in the previous part. That gives us an overall probability of 0.4828. Please do the 15-5 homework in your assignment packet.